Swayam Prabha. Digital India. Educated India.
Good morning and welcome again. This is lecture 28 and we'll primarily be discussing multiple nuts. Last time I had posed two questions. The first one was pertaining to the order 4 normalized basis function. In particular, I asked you, why is it that we'll have to let go of the C2 continuity condition if I move not T1 to not T2, making T2 a multiple knot of multiplicity 2. Let's try to address this slightly differently. First, a little recap. Let's look at the number of unknowns and the number of conditions available to us for an order 4 B-spline basis function for simple knots T0, T1, T2, T3, T4. We got three conditions here, making it 6. This is the seventh one, plus 3, 10, plus 3, 13, plus 3, 16. Conditions here. And if we look at each of these individual cubic polynomials, phi 0, phi 1, phi 2, and phi 3, in general, phi I being given as ai plus bi times t plus ci times t squared plus di times tq, I going from 0, 3, we have 1, 2, 3, 4 times 4, 16 unknowns. 16 conditions, 16 unknowns. This system is solvable. Now, if I move T1 to T2, I let go of this knot span, and because of which I'll probably have to let go of one of these conditions. As I mentioned, most likely it is going to be C2 continuity condition at this junction point where we have multiple knots. T1 equals T2. Let's try to formally determine that it is only the C2 condition that, if we let go, would make sense to us. Now let's look at these phi's one by one. Phi 1, let me write this thing as a0 plus a1t plus a2 t squared plus a3 tq. Clearly, because of these three conditions, I'll have a0, a1, and a2, all of them to be equal to 0. So phi 1 will be equal to a3 tq. Even if I have moved T1 to T2, I will not be letting go of the C0 or position information here. In a sense, the position information will still be valid. When I move T1 to T2, I would not know what phi 1 is. Let me ignore this for now and straight away come to phi 3. Phi 3, if I write this thing as d0 plus d1t plus d2 t squared plus d3 tq, phi 3 at T4 this knot here, will be greeted by these three conditions. And remember, nothing has happened in the vicinity of T3. In a sense, the position, slope, and curvature continuity conditions still exist at this junction point. So I would say that phi 3 can be uniquely determined. Because of these three conditions and the fourth condition over here, I would say that even phi 0 is known to us. Now let's come back to phi 2. I write phi 2 as C0 plus C1t plus C2 t squared plus C3 tq. T3 is again a simple knot. These three conditions are available to us. And what will happen when T1 moves to T2 is that this junction point will move to this one. In a sense, the position information at these two junction points will be identical. So we have three conditions and the position condition here, which would mean that even phi 2 will be known to us. Now let's try to figure what happens to phi 1. There is a minor typo here. This thing should be phi 0 and not phi 1. Coming back to phi 1, let me express phi 1 as a cubic polynomial, since this is an order 4 B-spline basis function. So phi 1 is b1 plus b2 t plus b3 t squared plus b4 tq. Doesn't matter what choices or coefficients you take, b0 to b3 or b1 to b4. Now let's try to figure the conditions which are available for phi 1. Remember, after having moved T1 to T2, the position information is the same. Let's write it. So phi 1 at T1 equals b1 plus b2 T1 plus b3 T1 squared plus b4 T1 cube. Phi 1 at T2, which is the same as T1, will have the same position and the same equation. How about the slope? Phi 1 prime at T1 equals b2 plus 2 times b3 T1 plus 3 times b4 T1 squared. This is the slope, and the second derivative, phi 1 double prime of T1, will be equal to 2b3 plus 6b4 at T1. Let's say this has some value, b1. This has another value, let's say b2. As I mentioned earlier, the position here and here, that means the ordinates, they will be the same. And let me represent those ordinates by phi a. Now, if you notice, of these four equations, the first two are identical. What would that mean? This would mean that I'll have to let go of one of these b's, either b1 or b2 or b3 or b4. Now, which one do I let go of is something that is not clear to me as yet. I cannot presume beforehand that phi 1 will be quadratic or phi 1 would be cubic or anything like that. But one thing is for sure, I'll have to let go of one of these unknowns. What would that mean? That would mean that I'll have to let go of one of the three conditions at this junction point. Now, which one do I let go of? I'll have to retain C0 condition because that is used to determine phi 0 completely. Now, I'll have to either let go of C1 or C2 condition. Amongst the two, it has to be the C2 condition that I'll have to get rid of, simply because if I say that my spline is not C1 continuous over here and it is C2 continuous over here, that does not make sense. For a function to be C2 continuous at any point, it has to be C1 continuous at that point. So between these two, I'll have to retain C1 continuity. I'll have to let go of this C2 continuity condition here. That answers the first question in the previous lecture. Now let's investigate multiple knots further using a simple example. An example which was an assignment problem to you in the previous lecture. So this is a quadratic spline that we are trying to construct for the knots given to us 0, C, this value at this time is in between 0 and 1, the third knot 1, and the fourth knot 2. It stands over 3 knot spans. So clearly it will have 3 segments, phi 0, phi 1, and phi 2. And each of these segments will be quadratic, pure quadratic polynomials. How about the conditions that we'll be needing? We'll be needing phi and phi 1 both as 0 here, phi and phi 1 again both as 0 here. These are 4 conditions, and the fifth one will be integration from 0 to 2 phi of t dt will be equal to 1 over 3. 3 is the order of this B-spline function. This investigation is about what happens when C becomes 1. In a sense, what happens when this knot moves to this position over here. We'll try to figure this thing out mathematically. Let's start constructing phi 0, phi 1, and phi 2. First, phi 0. I'll write phi 0 as a0 plus a1 t plus a2 t squared. I'll be skipping some steps here. So these two conditions will imply that A0 is 0 and A1 is 0. So phi 0 will be A2 t square. Let's ignore phi 1 for now and jump to phi 2. And let's be a little smart. I can write phi 2 as, say, d0 plus d1t plus d2t squared, or realizing that two of these conditions, the position, the slope, they're both 0 over here at t equals 2, I can rephrase this quadratic polynomial without any loss of generality. I can rephrase phi 2 as d0 plus d1 t minus 2 plus d2 t minus 2 the whole square. Just that the 3 d's over here will be different from the 3 d's over here. Let me use this expression and employ these conditions to find that d0 will be 0 and d1 will also be 0. So that phi 2 is equal to d2 t minus 2 the whole square. Let me save these results for us to use later. Phi 0 is a2 t squared. Phi 2 is d2 t minus 2 squared. Let's come now to phi 1. Phi 1 equals C0 plus C1t plus C2 t squared. Phi 1 has to be a quadratic polynomial again. And let's try to find what C0, C1 and C2 are. By the way, these symbols may not be good for us to use because we are using the symbol C to represent one of the nuts. So there might be some confusion later on. So let me rephrase phi 1 to be b0 plus b1t plus b2 t squared. Since C at this time is a simple nut, I can use position and slope continuity at this junction point. Remember, this is a quadratic B-spline. Order is 3. So at any point over it, the spline has to be C3 minus 2, that is C1 continuous. So these are the two conditions available here, and there would be a position condition available over here. 3 conditions, 3 unknowns, b0, b1, b2. I should be able to uniquely find phi 1. Let me represent this junction point by symbol B and this one by symbol X. So at B, we have b0 plus b1 Now the t value is c plus b2 c squared equals phi 0 at c, which is a2 c squared. This corresponds to position continuity, and for slope continuity I have b1 plus 2b2 evaluated at c will be equal to 2 times a2 evaluated again at c. So this is the position continuity condition at junction B, and this is the slope continuity condition at the same junction. Now let's express B1 and B0 in terms of B2. So B1 is 2 times A2 minus B2 times C. Substitute for B1 here. You'll get B0 equals A2 minus B2 C squared minus B1 times C. B1 is 2 times A2 minus B2 C, and 1 C comes from here, so we'll have C squared. This simplifies to minus A2 minus B2 C squared. Let me write phi 1 here now. This would be minus of A2 minus B2 C squared plus 2 times A2 minus B2 CT plus B2 T squared. Now overall, how many unknowns do we have? We have A2, we have D2, and we have B2. What are the conditions that we may have missed? We have missed the C0 and C1 continuity conditions at this junction point X. Let's work with them. Now C0 at X would give us from phi 1 we'll have minus A2 minus B2 C squared plus 2 A2 minus B2 C, the T value is 1, plus B2, again the T value is 1, and this would give us D2 if I substitute T as 1 here. Likewise, C1 continuity at X will give us, I'll have to differentiate phi 1 and phi 2, both 1s, with respect to T, and evaluate both at T equals 1. When I do that, I'll get 2 times A2 minus B2 C, this T goes off, plus 2 B2 T is 1, and this would be equal to 2 times D2 T minus 2. For T equals 1, T minus 2 will be minus 1. I'll let go of this with a minus sign. You would realize 2 is common So I'll let go of 2 from these terms. The idea here is to express any 2 of the 3 unknowns in terms of 1 unknown using these 2 conditions. Now let's add these 2 equations together, which would eliminate D2. So when I do that, I have minus A2 minus B2 C squared. If I add these 2 guys together, I'll get 3 times A2 minus B2 times C plus 2 B2 equals 0. This is an equation in terms of A2 and B2. Let's start clubbing the coefficients pertaining to A2 and B2 separately. So we have A2 times minus C squared plus 3C, and corresponding to B2 we have C squared minus 3C plus 2. This would be equal to 0. I would be able to write B2 now in terms of A2. You can realize this expression can be factorized. So B2 is A2 times C times C minus 3. This thing is going to the right over let me write this thing in the factor form, C minus 1 times C minus 2. So I have obtained B2 in terms of A2. If I substitute for B2 here and here, I'll get D2 in terms of A2. I would need the term A2 minus B2 as well. Let's work both of them out. First, let me work on what A2 minus B2 is. So A2 minus B2 equals C minus 1, C minus 2 minus C, C minus 3 over C minus 1, C minus 2, with A2 commoned out. Let me simplify this. This would be equal to A2 C squared minus 3C plus 2 minus C squared plus 3C over C minus 1 C minus 2. So this would be A2. These terms cancel out. 3C cancels out with minus 3C as well. All I'll be left with in the numerator will be 2 over C minus 1 C minus 2. I would need this result and this result to get D2. So now D2 equals A2 minus B2, which is 2 A2 times C over C minus 1 C minus 2. I'll have a minus sign here, plus B2, which is A2C C minus 3 over C minus 1 C minus 2. Let me block B2 for now so that I don't disturb it, and let me try to simplify for D2 over here. So minus of D2 equals A2C are common, and so is the denominator. And I'm left with 2 plus C minus 3. Now this is C minus 1, which cancels out with this one here. So D2 will be equal to minus A2C over C minus 2. Let me block this result also. Now that we have D2 and B2 in terms of A2, let me write phi 0, phi 1 and phi 2 in terms of a single unknown. So phi 0 equals A2 t squared, phi 2 equals D2, which is minus A2 C over C minus 2 T minus 2 the whole square. And now phi 1 equals minus of A2 minus B2C square. We have what A2 minus B2 is. So this is minus of 2 A2 over C minus 1 C minus 2. We have a C squared term here, plus 2 times A2 minus B2, which is again 2 times A2 over C minus 1 C minus 2 times CT. Let me see if I got all terms over here. So 2 times CT, and then A2 minus B2 is 2 A2 over C minus 1 over C minus 2. Seems okay. Plus B2, we have B2 right here, A2C C minus 3 T squared over C minus 1 C minus 2. So far, so good. We have all phi's, which by themselves are pure quadratic polynomials in t in terms of a single unknown a2. How do I find a2? We use this condition, that the area under this function over the knot span over which it stands is equal to 1 over 3, essentially non-zero. To compute this integration, we'll need three results. One, integration of phi 0 over this interval. Second, integration of phi 1 over this interval. And third, integration of phi 2 over this interval. So integral phi 0 dt from 0 to c equals a2 t cube over 3 0 to c, which is a2 over 3 c cube. Let's work for phi 2 now. Integral 1 to 2 phi 2 dt equals minus a to c over c minus 2. Integral of this would be t minus 2 the whole cube over 3 evaluated at 1 and 2. This would be equal to minus a to c over c minus 2. Let me have 1 over 3 here. For t equals 2, this is 0, minus for t equals 1, this is minus 1. So this is equal to minus a2c over 3 c minus 2. Now this one would be a little complicated. Let's try it out. Integral from c to 1 of phi 1 dt equals, let me denote this denominator by capital D to make my algebra a little easier. So I have minus 2 a2 c squared over d. I'll introduce t here because of integration, and because of these limits c to 1, that'll be 1 minus t plus 4 a to c over d, which is this term here. This t will become t squared over 2. And t squared, if I evaluate pertaining to these limits, will become 1 minus t squared. 4 over 2 is 2. About the third term, we'll have a to c, c minus 3 over d, t cube over 3, and t cube when evaluated at these two limits will give us 1 minus By the way, this is C here. Now let me have you do the algebra from here on. And let me skip a few steps to just tell you that integral 0 to c phi 1 dt, phi 0 dt plus integral c to 1 phi 1 dt plus integral 1 to 2 phi 2 dt equals 2 over 3 a2c. It turns out to be a very simple expression, and this is equal to 1 over 3 from this condition, which would imply that a2 equals 1 over 2c. Let me block this. Now try substituting for a2 in these three expressions. What do we get? Phi 0 becomes t squared over 2c phi 2 becomes minus 1 over 2 c minus 2 t minus 2 the whole square a2c there is half, so minus half c minus 2 t minus 2 squared. We are okay, and I'll have you figure out what happens to phi 1 if you substitute for a2 in this expression. Now let's observe the behavior of these three pure quadratic polynomials. For values of c not equal to 1 and for values of c equal to 1 at a later stage. Let's see how this behaves. We'll work with a small MATLAB code. Now this here on the right is a MATLAB code that I have written. You can see the expressions for phi 0, phi 2 and phi 1 here. I have initially chosen the not value c as 0.5 and a2 is given as 1 over 2 over c. Let's see how phi 0, phi 1 and phi 2 behave for this not value. You will observe a nice C1 continuous basis spline. The curve in red is phi 0, the curve in green is phi 1, and the curve in blue is phi 2. The not value 0, c equals 0.5, the not value 1, and the not value 2. Now let me increase this so that c becomes closer to 1. Let me use a value 0.7 and execute the code again. You would observe the change in the shape of this B-spline function. This junction point here corresponds to c value equals 0.7. Let me further increase this value. Now this junction point here is getting closer to this one. And you would observe this portion is now trying to develop a peak. Now with C equals 0.9, the peak is trying to get a little more dominant here. Maybe C equals 0.99, which is very close to 1. Now you see a clear peak. Not quite, though. You still, if you observe closely, would see a little green patch here. Now for this value, let's try to get the expression for phi 0, phi 1, and phi 2. Phi 0 looks like 50 over 99 times t squared. Phi 1 looks like some complicated coefficients, but it is still quadratic. And of course, phi 2 will be quadratic as well. Let's try to now make this c value very close to 1, but not quite 1. You see a clearly defined peak here. At this junction point, initially you would observe that the B-spline basis function was C1 continuous. Now you would see or clearly observe slope discontinuity here, but position continuity is still maintained. You would also observe that the green segment has vanished. It's only phi 0 and phi 2 that remain. Well, has the green segment vanished? Let's find out. So we have phi 0 again as a quadratic, phi 2 again as a quadratic, and let's see what the values for phi 1 are. I'm storing the values of phi 1 in the array y1. It so happens that all values of y1 are equal to 0.5. It seems like a constant function. But if you look at the expression for phi 1, it will still carry the term t squared. Now if I plug in c equals 1 straight out, making t equals 1 a multiple knot, and if I execute the code, we clearly see slope discontinuity here. The expression for phi 0 is half of t squared. That of phi 2 is half of t minus 2 squared. And that of phi 1 is minus of infinity. Is that so? You might want to check what happens to phi 1 at this junction point. This is the expression for phi 1 here. Phi 1 equals minus 2 times a2 times c squared plus 4 times c times a2 times t plus a2 times c minus 3 times t squared, the entire thing over c minus 1 times c minus 2. Here a2 equals 1 over 2c, or twice a2c equals 1. We would like to see what happens to phi 1 when c is equal to 1 and when t is also equal to c, which is equal to 1. At this time, you would observe that this factor c minus 1 would offer a singularity to phi 1. Let's simplify this expression further. If we substitute for twice a2 times c equals 1, we have phi 1 equals minus c, 2 a2 c is 1, plus I have 2 a2 c is 1 t, plus this becomes half c minus 3 t squared over c minus 1 c minus 2. Now first, we should know that the values of t are permitted to be in between c and 1. This is the closed interval on the left, open interval on the right. When c is equal to 1, all this parameter t can take is the value equals c, which is 1. So let's substitute t equals c here. This is minus c plus twice of c plus half c squared times c minus 3 over c minus 1 c minus 2. This is equal to, this would become c times 2, 2c plus c cubed minus 3c squared over twice c minus 1 c minus 2. This would be equal to, I can take 1c common. This is c squared minus 3c plus 2 over twice c minus 1 c minus 2. Now if you notice, the numerator here is nothing but c minus 1 times c minus 2. So phi 1 evaluated at t equals c is equal to c over 2. And when c is 1, this would be 1 over 2. So even though the MATLAB code was giving phi 1 as minus infinity, when c was equal to 1, this analysis shows that that is not quite so. Phi 1 at t equals c equals 1 is finite and is equal to half.